Algebra 2, Chapter 15, Section Sequences. A sequence, in the context of mathematics, is an ordered list. Okay, so it's got order. In other words, the sequence 1, 2, 3 is not equivalent to 3, 2, 1. The order matters. And when we're talking about sequences in this class, we're going to be talking about sequences of real numbers, but we could put any kind of object in our sequence. This is different than a set, which is unordered. Remember, we could have a set of numbers, and the order in the set doesn't matter. 1, 2, 3 is equivalent to the set containing 3, 2, 1. Think of a set like a bag. Remember I say Santa's bag. It's a bag that the orders doesn't matter. It could have nothing in it. It could have infinite number of things in it. That's what a set is. As we saw in the previous section, sequences use subscript notation to refer to entries in the sequence. So for an arithmetic sequence we're about to talk about, we might have a sub 1, comma a sub 2, comma a sub 3, comma to a sub n. We use the subscript notation to indicate the different entries in the sequence, or terms in the sequence. An arithmetic sequence is a sequence with a difference between the pairs. The arithmetic difference, the subtraction, is constant. So for instance, just real quick, this is an arithmetic sequence 1, 2, 3, and so on, because the difference between each number is 1, which is a constant. So let's find the first 3 terms and the 20th term of each of these sequences. And each of these sequences has got a general formula. We just need to plug in and find the output. It's almost like a function. So a sub 1, the first entry would be put in 1 for n. So we have 2 minus 5, which is negative 3. A sub 2, put in 2 for n. 2 times 2 is 4, minus 5 is minus 1. A sub 3 would be 2 times 3 is 6, minus 5 is 1. And a sub 20 would be put in 20, we get 40 minus 5 is 35. And notice this is an arithmetic sequence. The difference between each entry is 2. This is a constant. These other 2 series sequences, will not be arithmetic. So b sub n is n plus 1 over n. So what's the first term of the sequence b? Well, we put in 1, we get 1 plus 1 is 2, divided by 1 is 2. B sub 2, we put in 2, we get 2 plus 1 is 3 over 2 is 3 halves. B sub 3, put in 3 and we get 4 over 3. And b sub 20, put in 20 and we get 21 over 20. This is not arithmetic. The difference is changing between the different values. And you might notice this is similar to functions, but for a sequence, we can only have entries that are discrete. So there's no a sub 1.5 because there's not a 1.5 entry in the sequence. These are indexes in our sequence. Okay. So c, we have c sub 1. So we take negative 1 to the first power, which is negative 1, and multiply that by 1 squared, which is 1. Negative 1. C sub 2 will get positive 1, and 2 squared is 4. C sub 3 will get negative 1 again, and 3 squared is 9. So this is an alternating sequence. The sign is alternating between each entry, depending on whether n is even or odd. C20 is even, so the negative will go away, and 20 squared is 4,000. 20 times 20. 4,000. That sounds wrong. 400, sorry. 20 times 20 is 400, not 4,000. Helps to remember our arithmetic. So let's go back and think, what are these? Which of the following sequences are arithmetic? Notice we don't say arithmetic, arithmetic. So which of these sequences is arithmetic? We need to look at the distance or the subtraction of each pair, consecutive pair in the sequence. Here, the difference is -4, -4, -4, -4. So yes. And we might even have a variable for this distance, -4, which we'll call that the distance between them. Here the distance is 2, 4, 8, 16, 32. The answer here is no, it's not arithmetic. Here the distance between these, when we subtract, the p's will go away. 5 plus p minus 2 plus p will be 5 minus 2, p minus p, which would be p minus p is 0, 5 minus 2 is 3. Here, 8, 5, 3, 3. The distance is 3 between them all, so the answer is yes, it's arithmetic. Here the distance is 5, 5, -5, -5. Actually, I said that backwards. -5, -5, 5, 5. So it goes down 5 twice, up 5 twice. This is not arithmetic, because it's not the same number for all of the entries. For positive n, the nth term of an arithmetic sequence is a sub n equals a sub 1, which is the first term in the sequence, plus n minus 1 times d. Okay, so basically we're going to add d n minus 1 times to the initial thing. Why n minus 1? Because we don't add it the very first time, and we're starting our indexing at 1. Okay, so d is our difference between consecutive terms, which is the sign difference, not the absolute difference. When you subtract the second thing from the first, that's how you get d. And this gives us a formula to find just any entry in the sequence, knowing the first thing and knowing the distance. Okay, the n is here that we put in, so the n is going to be a given. So for the arithmetic sequence 5, 9, 13, ... find the 10th term. So a sub 1 is 5, the first thing in the sequence. The distance is 4. And to find the 10th term, a sub 10, all we need is to take a sub 1, 5, and add to it n minus 1, which is 9, times the distance 4. 9 times 4 is 36. Do the addition and we get 41. And we're done. So that's why having a general formula for a sequence is so very handy, because we can just plug in and get our answer without having to find a sub 2, a sub 3, a sub 4, and so on. A car dealer leases a slightly used demo car, meaning a demonstration, not a demolished, demonstration car, with 5,000 miles on the odometer, and includes an annual mileage restriction of 15,000 miles per year. Write a formula for the odometer restriction at the end of the nth year. So this is another arithmetic sequence. Our starting value would be 5,000 miles. That's how many miles are already on the car. Each subsequent year we can put 15,000 miles on the car. So our restriction after the nth year would be 5,000, the original, plus 1 minus n times the distance, 15,000. B, if the lease expires after 6 years, what is the odometer restriction when the car is returned? In other words, what is... Well, this is a little tricky, so at the end of the nth year... Yeah, see, this is tricky. I messed up a little bit, because this is the initial number of miles. Okay, so 5,000 is kind of more like a sub 0. And we started our indexing at 1, not at 0. Okay, so at the end of the first year, we would owe, there would be a restriction of 20,000, because we have 5,000 plus the 15,000 at the end of the first year. And so at the end of the nth year, it's 20,000 plus 1 minus n times 15,000. That fixes that for us by just changing what a sub 1 is. So a sub 6 now would be after the 6th year, 20,000 plus 6 minus... I wrote this backwards, sorry. N minus 1, not 1 minus n. 6 minus 1 times 15,000. So 6 minus 1, of course, is 5. 5 times 15. gives us 75,000 plus 20,000. It's a total of 95,000 miles that we can have on the odometer, or less, at the end of the lease. Plot the values of the sequence a sub n. This is a similar sequence to what we just saw, although it starts at 5,000, not 20. And then graph the function 5,000 plus 15,000x in the same axes. So here is n, and here is either a sub n or f of n. Okay? So putting n in, we wanted to look at different discrete values. So 1, 2, 3, 4, 5. And if we wanted this to match the example, oh, this does match because we're graphing, right? So we put in 1, we get 5,000 plus 15,000 times 1. So here we've changed the formula by multiplying out the n minus 1. So we have 20,000 plus, and then doing the distribution, 15,000 n minus 15,000, which gives us 5,000 plus 15,000 times n. So here this is the same formula, and then we're going to graph this very similar rule. So the plot at a sub 1, we had 20,000. And I'm going to write this in thousands. So that's 20,000. At a sub 2, we added 15,000 to that. So this is 40. We end up at 35,000 at a sub 2. 20, 40, 60, and 80. Okay, so after 35,000, we have 15,000 more, is 50,000. So at a sub 3, we have 50. At a sub 4, we add another 15 to get 65,000. And then we add another 15 to get 80,000 at 5. Okay, and this looks very much like a straight line, right? Although when we plot, we only have the points that are inputs that are allowed to a sub n. So there's discrete points. Now if we plot f of x on the same axis, then we have a y-intercept of 5,000. Okay, let's use blue. And then we'll have, from here, we'll go up in a line with a slope of 15,000 rise over run, which will be continuous. So we would draw a straight line, and you can see my dots aren't perfectly straight, but it would look something like this. Find the first 4 terms of the sequence a sub n is a sub n minus 1 plus 3. So here we have the sequence defined recursively, not generically. So we're defining the nth term on the previous term. So a particular term is the previous term plus 3. So find the first 4 terms of the sequence and the nth term when a sub 1 is 5. So a sub 1 is 5, a sub 2 is, and this is why it's recursive, a sub 2 is a sub 1, 5 plus 3, which is 8. A sub 3 is 8 plus 3 is 11. A sub 4 is 11 plus 3 is 15. And the nth term then would be given by the same formula as an arithmetic sequence, because this really is arithmetic. Sorry, that's spelled wrong. So we would have 5 plus n minus 1 times the distance between, which is 3. Now let's find the first 4 terms of the sequence. A sub n is 3 times a sub n minus 1. So a sub 1 is 4, a sub 2 is 12. A sub 3 is 12 times 3, which is 36. A sub 4 is 36 times 3, which is going to be a bigger number. We might need a calculator to find that. 108. Okay. So we see each time we're multiplying by 3. So if we think of a formula, that's a little bit tricky here, but we would have the original value 4 times 3 to the power of n minus 1. So when we put in 1, we get 0. 3 to the 0 is 1. 1 times 4 is 4. When we put in 1, we get, when we put in 2, we get 3 to the first, which is 3 times 4 is 12. When we put in 3, we get 3 squared. 9 times 4 is 36. So this, if you think of this, this is 4 times 1. This is 4 times 2. 4 times 1, 4 times 3, 4 times 9, 4 times 27, which is equal to 4 times 3 to the 0, 4 times 3 to the first, 4 times 3 squared, and 4 times 3 cubed. So that's where this general pattern comes from. The Fibonacci sequence is defined recursively. F sub 1 is the same as F sub 2 is 1. Okay, so our sequence starts 1, 1. And then F sub n equals F sub n minus 1 plus F sub n minus 2. So we take the previous two numbers, add them together to get the next one. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Find F sub 10. So here's 1, 2, 3, 4, 5, 6. 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, and 21 plus 34 is 55. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So F sub 10 is 55. Now it says show that F of 2 sub n equals, F of 2 times n. So equals the Fibonacci number at n plus 1 squared minus the Fibonacci number index n minus 1 squared. So when n is 5. So when n is 5, we're trying to show 5 times 2 is 10. Trying to show f of 10 equals 5 plus 1 is 6. F of 6 squared minus f of 4 squared. So f of 10 was 55. F of 6, 1, 2, 3, 4, 5, 6 is 8. And f of 4 is 3. 8 squared minus 3 squared. 8 squared is 64. 3 squared is 9, which equals 55. So, sure enough, it's true for this. And this is actually an actual identity. It's true everywhere, although we can't prove that in this class. We can just rely on that it's true.